Here's your mini lecture for 10.1.4 Integrated 3. It's summation notation and combinations of series. So it says, so far in this chapter, you focused your work on arithmetic series represented algebraically, geometrically, and graphically. Today you will be introduced to new notation for arithmetic series, and you will also look at methods for determining their sums. As you work today, keep the following questions in mind to focus your team discussions. How does this connect to what we've done before? How can we simplify it? And how can we describe it? So if you remember, an arithmetic series is a series that goes up by a certain amount every time. It can be represented as a line, as it's linear. It's like y equals mx plus b. There are other series in the world besides arithmetic series that we haven't talked about this year yet. But this one here is going to be an arithmetic series. So it says, remember Gauss, the mathematician from 10.1.3, whose teacher tried to keep him busy by asking him to add up the numbers from 1 to 100. Legend has it that Gauss did not show any of his work, but he is commonly said to have used a method that starts with the steps below. So everybody look at this. Hopefully you'll notice that this bottom one, it is the same thing as the top one, but they wrote it backwards. All these numbers in between are just, well, they're the numbers in between, but this one's going the other way. But you'll notice that these pairs all add up to 101. And s plus s is 2s. So really, if he knew how many pairs there are, then he would just be able to find however many pairs there are and then divide by 2, which is what we've kind of been doing. We've been saying take the first thing plus the last thing and then multiply by half, or multiply it by the amount of pairs there are. So it says, how can you simplify it? Let's not do that part yet. Show it on your paper. So this is like the same thing as when we write n over 2 and then first plus last. Because see, all those 101s on there, those are what happens with the first term plus the last term. And they're even the second term and the second to the last term, if you line them up like this, they always add up to the same amount. So this is just that same formula we've been using this whole time. It's just another way to show it. You can show it as adding the series to itself backwards, if that makes any sense. So now we're going to go ahead and do letter D. So letter D says, use his strategy to calculate the sum of the series below. Show all of your work. So we have lots of strategies now. We can just plug our formula in, or we can draw that graph that has like the little bars, and you take the bars and make a rectangle. But now we have this other strategy. This is Gauss's strategy. So it wants us to take this and use Gauss's strategy to sum it up. Is that what it said? Yeah, to show this, calculate the sum of the series. So first we want to write it right side up, or if that makes any sense. We want to write it forward. So we know it starts with a 2 and a 5 and an 8 and 11, dot, dot, dot. I can tell that it goes up by 3 every time. So that's why I wrote a little formula for it. I wrote an equation. The slope is going to be 3. And the y-intercept, if I went backwards, if I'm adding 3 every time, what plus 3 equals 2? Well, negative 1 plus 3 equals 2. So that's how I can find out. I want to know how many terms there are so that I can, because what I want to do is I want to write this thing forward And they gave it to me mostly, but they're just missing a few of those little pieces. And then I also want to write it backward. And then I want to add them up. S plus S is 2S. And all these pairs are going to add to 61. Actually, you didn't even really need to find out the rule for this, because you could have just, at least you had that 59, and that would have added to the 2, and you got your 61, and all these other ones in between are going to add to 61. But I just found the rule so that I could, write a few more terms. Actually, you don't even need to know how many terms there are, because his method will still work. Okay, so I summed it all up, and then what? Then let's get this going. Yeah, then I put it in my formula, the one that goes first plus last. So here's my formula. I found out there's 20 terms. I put the last term in, and then I solved it for x by adding 1 to both sides. I found out there's 20 terms. And then, so if there's 20 terms, I have 61 times 20, because there's 20 of these. But then I have to divide by 2 because of this 2 over here, because it says 2s equals, whatever those add up to, which is 1220, and I get 610. Okay, I want to move on to 1051, and this will be a 2-part series here because I'm not going to make it through in time. I've got trying to go for 10 minutes here. So it says the series in part D of problem 10-50 can also be represented using summation notation as shown below. So this thing right here is a sigma. It's a Greek letter, and it indicates that the terms generated as C, they called the term C instead of N or X, changes from 1 to 20. So it's like the first term plus the second term all the way up to the 20th term. Here's an expression for that, and this expression is called the argument. Another expression for this could be like y equals mx plus b. The slope is 3, and the y-intercept is -1. If I were to distribute this 3, I'd have 3n minus 3 plus 2, which is 3n minus 1. And you can tell that these are going up by 3 each time. So that's called the argument right there. And then they're showing it in a table. And then this letter down here is called the index. So you can use any letter of the alphabet for an index. I noticed that we like to use N's and I's. Sometimes I'll see a K. But really you can use anything. You can use P or you can use T. So in this one they're using C. It's just the input. The series may also be written with a different starting value and corresponding rule. So I could start from the 0th term and go to the 19th. Instead of starting from the first term and going to the 20th term, I can go from the 0th to the 19th term. Okay, so I know that probably didn't make sense, but we're going to try letter A and letter B. So letter A says, use summation notation to represent this series, 15, 19, 23, 27, 31. So this is 1051, letter A. Okay, so there it is. So it's 15, 19, 23, 27, 31. So I just went ahead and got a y equals mx plus b for it. That's my favorite way. I see it's adding 4, so that's the slope. The y-intercept would be the 0th term, so 15 minus 4 gave me 11. Or I could write it as the first term plus the slope times n minus 1. Okay, these are both of the same thing, because if I distribute the 4, you'll see that I'd get 4n minus 4 plus 15 is also equal. They're the same thing. Okay, I like to use this form best, the y equals mx plus b form the best. So I can go ahead and generate all the terms. So I know the first term is 15 because 4 times 1 plus 11 is 15. 4 times 2 is 8 plus 11 is 19. See how you can just do that? 4 times 3 is 12 plus 11, give me 23. So you can generate the terms. This would be 27, this is 31. So that's what they told me to do in letter A. They said use summation notation to represent this series. So I did. So basically you just write this funny shaped thing, this sigma. You say where you're starting and ending at, so the first term to the 5th term, and then you write this argument here. Okay, and this is your x value. It's your index. Okay, and then letter B says, how can you use your expression to write an expression for Lorna's complicated series using summation notation? Oh, sorry. It's letter B. Write the series out and calculate its sum. So letter B, here's the series. I can generate each term just by plugging this number in for t. T squared. So 1 squared, 2 squared, 3 squared, 4 squared, 5 squared, 6 squared. So, and then I wanted to sum it up, so I was too lazy to get out my calculator, and I just took the first term and the last term, and I got 37, and I knew that there was 3 pairs, and I went 37 times 3, and it didn't work. Why didn't it work? Because there's some series in the world that are arithmetic. Is that a y equals mx plus b? No, that is not a linear. That's not a linear. If it was a function, it wouldn't be a linear function. So just on this one, you just have to use your calculator. You have to go 1 plus 4 is 5 plus 9 plus 16, and you'll actually get 91. Now I'm going to do part 2. I'll end this one, and I'll do another couple problems for part 2.